Welcome to what is to be the first of a series of virtual classes that are going to be offered online, obviously dealing with our current situation. So, a couple of things that I just want to draw to your attention. So all classes, at least for the foreseeable future, are going to be offered in this format, where it will be a pre-recorded lesson that you will be able to watch on your own time and then go back and ask questions about on our scheduled class day. So today is it's listed as Tuesday, March 31st, but I'm actually recording this on March 30th. I'm going to post this session today with the hope that you will watch it by tomorrow and you will be ready to ask any questions that you have. Question answering will be done either using a Schoology session on like we did this morning for the quarterly, or using a Zoom session, which will not be recorded, but will be offered several times throughout the day tomorrow in about half-hour increments. All right, so as you can see, today we are going to start Unit 8, which is called States of Matter, and the focus of this unit is going to be primarily on one state of matter called gases. So we'll talk about that in detail today, or beginning today. And our first exam, and it says tentative, and that is a very tentative date for that. I'm not quite sure how fast we'll be able to go, or what pace we'll take as we go through this format, but I'm looking at somewhere around April 21st as our tentative date for that. The first lab, which will obviously be a virtual lab, is going to be somewhere around April 14th. And tonight you will not have any homework. I do just want to offer this clarification that Zoom sessions cannot cover new material. And the reason for that is because Zoom sessions cannot be recorded, I cannot teach new material because some students may not be able to access it at the time I'm teaching it. So all new material is going to have to be pre-recorded like this lesson. And those Zoom sessions will just be question answering sessions. We could do a practice problem if you have a question, very similar to what we would do if you stopped by my classroom before school or after school for extra help. So if you have questions, please feel free to continue to reach out through Schoology, through email if Schoology is down like it currently is as I'm recording this. And what we can do is schedule some Zoom sessions for some face-to-face learning to review any questions that you might have. But again, those won't be new material sessions. All right, let's move on then. Okay, so this next section, or this first section, is called Kinetic Molecular Theory, which, just like it sounds like, is about how molecules are moving around. If you think about the word kinetic, hopefully you're thinking about energy of movement. So the first part that you need to know is that right now we're going to assume that gases are composed of a large number of particles. So remember, they're separate from each other, so there's an enormous number of particles even in a very small sample. And they behave like hard spherical objects in a state of constant and random motion. So they're constantly bouncing around in whatever container they are confined to. The second piece of this, and again, I do encourage you, if you're watching this, to please be writing it down or typing it, because that helps kind of firm those connections in your mind. So the second one says these particles move in a straight line until they collide with another particle or the walls of the container. So if you imagine, if you have a particle that's moving around in some container, and I'll just draw a really quick container for you right here. So that particle is moving around inside of the container until it bumps into the walls of the container and then is deflected. Almost like a miniature game of Pong, where the container walls are what keep redirecting that particle. So these particles move in a straight line until they collide with another particle or the walls of the container. And the third part that we need to know about it is these particles are much smaller than the distance between particles. So if you imagine that this is my container up here, a particle is, and I couldn't obviously draw it to scale, but a particle is extremely small. And the distance between particles that are close to each other is still many, many, many times the size of the particle themselves. So when we talk about the volume of the gas, we're talking about the volume of the container, the space that the gas is confined to, not the volume of the molecules themselves. And that's going to become important later on when we differentiate between real and ideal gases. All right. If you have questions on any of these three, please, again, write down your questions so that I can answer it, maybe tomorrow during one of our Zoom sessions. So when we move on to the next page, we have a fourth piece that we need to think about. So the fourth piece says there is no force of attraction between gas particles or between the particles and the walls of their container. Now, we're going to find out this is not exactly true, and that's what's going to help us define what is meant by an ideal gas and how it is different than a real gas. So in reality, there are small forces of attraction, and they do actually affect the pressure of gases and the energy with which they collide with the walls of the container. But for our purposes, we're going to ignore any attractive forces between gas particles or between particles and the wall and the container wall. Number 5, collisions between gas particles or collisions with the wall of the container are perfectly elastic. That means no energy is lost when the two particles collide with each other or when a particle collides with the wall of the container in which it's confined. None of the energy of a gas particle is lost when it collides with another particle or the walls of the container. Again, something that is assumed in kinetic molecular theory, and it was later found to be not quite as true as we would like it to be. But for the purposes of our class and the calculations that we'll do in our class, it's a safe assumption that you can make. It's not 100% true, but it's not significant enough that it's going to affect our calculations. Okay, and the sixth and last point that I want to make is that the average kinetic energy of a collection of gas particles depends on the temperature of the gas and nothing else. So how fast the gas particles are moving in a container depends on the temperature that that gas is at. Obviously, the higher the temperature, the more energy they're going to have, the faster those particles are going to be moving. So now we are going to look at some information that will relate temperature and pressure of a gas. So if you look at the first line here, when you are working with gases, the temperature must be in Kelvin. Now, think about this for a second. We're going to be doing calculations with those gases. Celsius has negative temperatures, right? You could have Celsius temperatures that are below 0 degrees Celsius. So that doesn't work out very well when you're trying to do calculations, because you could wind up having a negative pressure or a negative volume, and that's kind of difficult to make sense of. So instead, what we do is we use an absolute scale where 0 Kelvin, also known as absolute zero, is theoretically the lowest possible achievable temperature, even though whether or not we've actually achieved it is debatable. But it's a scale basically that sets 0 Kelvin as the lowest possible temperature and then works up from there. So there are no negative temperatures here, and that works out really nice because then we don't run into the problem of having negative pressure or negative volume in our calculations. So whenever you're working with gases, even when a problem gives you the temperature in Celsius, please make sure to change that temperature into Kelvin before you begin to do any part of the problem. So, how do you change a Kelvin temperature into Celsius or a Celsius temperature into Kelvin? That's what we're going to look at right here. So they are related by this equation. So the Kelvin temperature is equal to the Celsius temperature plus 273.15. So if you think about this for a second, if I imagine that water freezes at, and I know if we were in class, all of you would say 32 degrees Fahrenheit, but we never use Fahrenheit in science because that's an English measurement. So we would instead say water freezes at 0 degrees Celsius. Okay, well, at 0 degrees Celsius, I'm just going to type this in here for you. So at 0 degrees Celsius, based on our relationship between Celsius and Kelvin. So that would be 0 plus 273.15. I'm ignoring significant figures for a second here. So we would get a temperature of 273.15 Kelvin. Notice that the Kelvin scale does not have a degree sign, so it's just 0 degrees Celsius is equal to 273.15 Kelvin. Now, if I jump all the way up to the boiling point of water, the boiling point of water in Fahrenheit, of course, is 212 Fahrenheit, but in Celsius, it's 100 degrees Celsius. I'm just going to do that again. So if I jump up here to the boiling point of water, that would equate to a Kelvin temperature of 373.15 Kelvin. Again, ignoring any significant figure rules for just this brief period of time here. So, pretty simple equation to go back and forth between Celsius and Kelvin. So now let's look at an example problem. So if I want to convert, this time we will worry about significant figures. If I want to convert 25 degrees Celsius to Kelvin, I'm going to plug in my 25 degrees Celsius here. I'm going to add 273.15 to it, and I'm actually going to get 298.15 Kelvin. However, accounting for significant figures, this has 1 decimal place here. This has 2 decimal places, so our answer is going to be limited to the 1 decimal place. So my answer of 298.15 will become 298.2 Kelvin. And we can do the same thing working in the other direction. So if I had a temperature that was in Kelvin, and for whatever reason the problem asked for a final temperature in Celsius, that would mean I would have to take my temperature and convert it back into Celsius. Now, sometimes you're going to get a problem that's going to give you a temperature in Celsius. It's going to ask for an answer in Celsius. Yet, to do the problem correctly, you're going to have to change it to Kelvin and then change it back to Kelvin at the very end of the problem. So just be aware, even if you are given a temperature in Celsius, you absolutely must, as it says up here, you must complete that problem while you're working in Kelvin. I cannot stress that enough because your answers will turn out to be wrong. All right, so if I'm working the other way, I'm going to rearrange that equation. So Kelvin, which was on the left side of the equation, I'm now going to subtract the 273.15. That'll leave Celsius by itself. So Celsius temperature is going to equal the Kelvin temperature minus 273.15. I know it sounds obvious, but whatever. So if I'm solving this, Celsius is equal to 310.5. That was what we were given in the problem, minus the 273.15. That gives us a temperature of 37.35 degrees Celsius, or when we account for significant figures, 37.4 degrees Celsius. Give you a minute to think about that for a little bit. Moving on to pressure. So we have units of pressure, and we have a lot of them, although we're not going to use all of them quite that much. So the first unit of pressure that I have over here is 101.325 kPa. So think about what pressure is. It's the force that's being applied to a specific area. So we're going to talk about pressure inside of a container because pressure is actually really important when you're dealing with gases. Pressure is not quite as important when you're dealing with solids and liquids because they're not moving around as much. They don't exert a whole lot of pressure, and they're not really susceptible to changes in pressure or temperature like gases are. So gases, which are highly compressible, they're going to be affected a lot by changes in temperature and pressure, where solids and liquids will not. So we don't really talk about pressure and temperature changes unless we're going through a phase change. We don't really talk about pressure and temperature changes when we're dealing with solids and liquids that much. So the first unit of pressure that we're going to talk about is in kPa. So the K should be familiar to us. It's the prefix kilo, just like we used way back in Unit 1 when we were going from meters to kilometers or grams to kilograms. So that prefix K is attached to the actual unit for pressure, which is called a Pascal. We don't use this pressure unit that often. However, you will see it occasionally in problems, so I wanted to make you aware of it. So that answer again is, or that unit of pressure is 101.325. All of these 4 units of pressure are set equal to 1 atmosphere, which is the unit that we're typically going to be performing problems under, but we'll see problems where we're above 1 atmosphere and below 1 atmosphere, so you'll see that. 760, and I put that decimal point there to keep the 3 significant figures. mm is another prefix that you're used to. It's called millimeters, and Hg is exactly what you think it is, which is mercury. So it's measured in millimeters of mercury. So if you imagine a setup where you have a almost like a U-shaped tube where one side is closed off and one side is open, the atmosphere is pushing down, and it is able to push down enough to lift that mercury that many millimeters, 760 millimeters. And then that was given a special name called torr. It's exactly the same measurement in acknowledgement of someone's contribution to the temperature scale, so or to the pressure scale. So that's why these 2 units basically are the same unit, but this is an acknowledgement of someone's contribution. The last thing that I'm going to mention on this page is something called standard temperature and pressure. So we will occasionally see a problem where standard temperature and pressure is referenced. In those problems, that is a shorthand way of giving you 2 pieces of information. So standard pressure is 1 atm, and standard temperature is 273.15 Kelvin. So if you're given a problem that says STP, that means they're giving you pressure and temperature in just those 3 letters. They're telling you what the temperature is, they're telling you what the pressure is. If it says just standard pressure, then they're telling you only 1.00 atm. If they give you just standard temperature, then they're giving you only the 273.15 Kelvin. Again, if you have questions, try and jot them down, and then I can answer them for you tomorrow during one of our sessions. Okay, so I mentioned earlier this idea that there was a difference between real gases and between ideal gases. For the most part, when we're working in class, we're going to work with what are called ideal gases, which means we're going to make a few assumptions. We're going to ignore a few things that are true just to make our calculation a little bit easier. So the first thing that we're going to ignore is that at high pressure and low temperature, a gas's kinetic energy can be insufficient to overcome attractive forces. That means at high pressure and low temperature, when those molecules are really close to each other, they actually do exhibit attractive forces. But we're going to ignore those forces because it complicates the equation so much that it doesn't affect the equation that much, but the math that goes into calculating the difference between a real and ideal gas is quite lengthy. And for the purposes of our class, it's not worth worrying about, especially now. And the second thing that we're going to ignore is the volume of the gases themselves. So it says gas particles themselves do have a finite volume, which must be corrected for in very precise calculations. However, we're not going to be doing those very precise calculations. In fact, they don't even do those precise calculations really in AP chemistry or even in the first year of chemistry in college. It's probably not until your 3rd year of chemistry when we actually started to worry about the difference between real and ideal calculations, real and ideal gases in our calculations. So it is not something that you're going to have to worry about for this class, certainly, and probably unless you become a chem major, it's not really something, or a physics major, it's not really something that you're going to have to worry too much about. Okay, so for this next part, I'm not sure how well this is going to turn out on the recording, but what I wanted to do was to practice some actual problems. So if you have difficulty seeing what this says, it says convert the following temperatures, 20 degrees Celsius to Kelvin. So in this case, there is a decimal point here, meaning I have 2 significant figures. So I'm going to take my 20 with a decimal point. I'm going to add the 273.15. So I'll get a total of 293.15. This is, remember, going from Celsius to Kelvin. However, since I'm limited to just 0 decimal places, here I have 2 decimal places, my final answer over here can have 0 decimal places. So my final answer is just going to be 293 Kelvin. For the second example, I have 285 Kelvin. So if you're typing this into a calculator, so I'm going to bring up the calculator here. Hopefully you can see that. If I have 285 Kelvin and I'm going to subtract 273.15 Kelvin, I'm going to get an answer of 11.85. Now, when you're looking at this, so if I have 285 minus 273.15, and I get an answer of 11.85, I'm still bound to significant figures. So with addition and subtraction, we look at decimal places. It says 0 decimal places, this says 2 decimal places. That means our answer can have 0 decimal places. So our answer in this case is going to be 12 degrees Celsius, again with no decimal places. Okay, for the next part, we're going to talk about pressure. This is the difference between my board at school and my board here, is that the numbers don't go with it. So pause for 1 second here. Okay, I'm back and I have erased those numbers. So this time we're going to do 2 practice problems that involve changes in pressure instead of temperature. So in the first practice problem I have 450.5 mmHg, or millimeters of mercury. I'm going to convert that into ATM. So I have 450.5 mmHg. Remember the conversion factor from a previous slide. There are 760 mmHg. Remember, if you want a unit to cancel out, that should go on the bottom. 760 mmHg, that was equivalent to 1.00 ATM. So into my calculator, I am going to type 450.5, and I'm going to divide that by 760. I don't need to do anything, obviously, with the 1 on top. So I get this answer. I'm going to pull this answer out here. We'll just stick it up here for now. So I have this answer, and it has a whole bunch of significant figures on it. I am limited to 3 significant figures. I have 3 significant figures here in my 760. I have 3 significant figures in my 1.00 ATM. I have 4 over here, but I'm limited to 3. So my answer of 0.5927 is going to become 0.593 ATM. My mmHg here and here will drop out. Okay, my final problem, and actually the final thing that will be on this recording, we have one more conversion, so we have 103.25 kPa, and we're converting that into mmHg. So I have 103.25 kPa times, if you go back to a previous slide, or hopefully you wrote them down, the relationship between kPa, which is going to go on the bottom, so we want to get rid of that, and mmHg is 760 points, so 3 significant figures, mmHg, 101.325, 6 significant figures, but it's not going to matter because we're limited to 3. So now I can type this part into the calculator. So for the first part, I have 103.25. I'm going to multiply by the 760 because that part's on top. I'm going to divide by the 101.325 because it's on the bottom. So I get this answer. I'm going to pull this out here. So I get that answer. And in this case, what I'm going to do, since I have 3 significant figures, and you can't see that because it's right on top of what I just wrote. So I have this answer down here, 774.438687. I'm only allowed to keep 3 figures, so this is multiplication and division. We're not looking at decimal places, we're looking at significant figures. So that's 774 mmHg. kPa drops out. Alright, so that's all for today. I am going to post this, and if you have any questions, I will be available during 4 different time slots tomorrow. You're free to join any of those time slots to ask questions if you have them. But please do me a favor and watch this video first. That way I know what questions you have and how to answer them. All right. Thank you all very much, and hopefully I'll see some of you tomorrow.